Good afternoon. This is Kian Chen from International Education Foundation. I'm here to present how to test the relativistic mass or energy concept in special relativity against the prediction by a new theory, asymmetry theory. First, some quick background. We all know about the momentum formula in Newton's mechanics, P equal to mv, which means the ratio of momentum to speed change is always a constant m. But Kaufman found this ratio of momentum to speed change actually increases with the speed of a particle. This picture clearly shows the difference between Kaufman's result against Newton's prediction. The particle accelerators later further proved this resistance to acceleration, which means when the speed of particle increases, the required momentum for same speed change increased dramatically, and it reaches infinity when the speed approaches light speed. Einstein tried to explain this phenomenon with his momentum formula, P equal to mv, but divided by a Lorentz factor. And you can call it relativistic mass or energy. It depends on how you explain this momentum equation here. Now, very interestingly, I found all the studies is only about the acceleration of a particle. So what happens if we are trying to decelerate a particle at a high speed? You may assume that it will be the same, right? But just keep this question in your mind for now. Now, let's have a quick introduction of asymmetry theory. We all know about this principle of constancy of the velocity of light from Einstein. So with some simple definition, as we show here in this picture, we can mathematically represent this principle as this equation 1 here. And you will be amazed how many groundbreaking results can be mathematically derived from this single equation 1 without making any other assumptions. So purely from these equations, we derive many groundbreaking results, which forms a comprehensive theoretical frame. And we named these results as asymmetry theory. So to summarize, right, asymmetry theory is just the mathematical result derived from the established principle from Einstein without any other assumptions. It's not that some crazy people throw up some crazy ideas. There's no assumptions or crazy ideas behind it. It's purely mathematics. Unlike special relativity, there's no paradox. It's comprehensive and self-consistent. And it's also in harmony with all proven experiments that we checked. You can see a list of examples here, right? Of course, it includes the Kaufman experiment. It also provides straightforward mathematical derivations of key physical formulas. So for example, we mathematically derive one single formula for 3 phenomena, including Doppler effect, cosmological redshift, and Cherenkov radiation. And of course, we also mathematically derive the formula for the mass-energy relations and resistance to acceleration. It also comes with a theoretical proof from Maxwell's equations, which I will present in April's meeting. Based on the prediction of asymmetry theory, we are going to present a design of experiment which should be able to tell if the theory is correct or not. Now let's focus on the electrodynamics of asymmetry theory. We mathematically derive this formula of momentum ratio to speed change as equation 2 here. VO is the velocity of the particle. So it's very important to see that the ratio of momentum to speed change actually depends on the direction of the velocity of particle. So in the case VO approaches the light speed, the momentum ratio becomes infinite, which means the speed can't surpass the light speed. In the case VO is perpendicular to C, we can mathematically derive this ratio of momentum to speed change formula here, equation 3, is equal to m divided by Lorentz factor. Very interesting and consistent with Kaufman. We can also mathematically derive this energy mass relationship, as you are all very familiar, E equal to mc squared. Now let's talk about where asymmetry theory differs from special relativity. Experiments clearly establish the resistance to acceleration, just like this picture of the ratio of momentum to speed change showed. Now, still remember the question, what will happen if we are trying to decelerate a particle, which means a particle at the same speed but different direction? If you believe in special relativity, either relativistic mass or energy, they are all directionless, which means the direction has no impact. So this picture should be the expected ratio of momentum to speed change based on special relativity, which is symmetric. But asymmetry theory made a surprising prediction. This is the formula that we mathematically derived for the ratio of momentum to speed change. As you can see, the ratio depends on the direction of the velocity of the particle, right? Which means the ratio will be different for acceleration versus deceleration. So this picture shows the difference of different theories, right? Newton predicts a constant ratio, while special relativity predicts a symmetric ratio, right? And asymmetry theory predicts a symmetric curve of ratio change, right? So that is one reason that we call our theory asymmetry theory. So asymmetry theory predicts that it's harder to accelerate a particle at high speed, but when you are trying to decelerate a particle at high speed, it's actually easier, not harder. So inclination to deceleration, that is the prediction of asymmetry theory, which is different from other theory. Now, based on this prediction, we can set up a simple experiment, right? We can make a particle travel at constant high speed, say 0.c. And then we can apply the same momentum, but in different direction each time. Repeat several times. We can measure the momentum to speed change ratio each time, right? So if special relativity is right, the momentum to speed change ratio should be constant because it has nothing to do with direction. If the ratio changes with direction, asymmetry theory is proven right. To summarize this presentation, resistance to acceleration is well established, but the case of deceleration is unknown. Special relativity predicts there's no difference for deceleration. Asymmetry theory predicts the dependency in momentum direction. So it predicts both resistance to acceleration and inclination to deceleration. Based on this prediction, a simple experiment is designed, which can clearly tell which theory's prediction is right. If you want more details of asymmetry theory, here are some links to the documents. And thank you. Any question?